Any questions or problems that we need to deal with right away? Otherwise, I'll pick up with this one where we left off. Okay, and we're still in chapter 3, unfortunately, with number 26. All right. Ammonium chromate. Isn't that nice of them? They actually give you the formula. Ammonium chromate. All right. We could do that ourselves. Chromate is a 2- charge. Ammonium's +1, so this needs to have 2. Right there. And we can get rid of the charges once we've got the compound written. The question is, what percent nitrogen by mass? Remember how we do that?
The molar mass.
Percent by mass. What we need is the molar mass of the element of interest. So see, we've got 2 nitrogens. Don't forget that subscript. 2 nitrogens. So we have 2 times 14.01 in the numerator. And then we have that also in the denominator. Plus what's next? 8 hydrogens. Oops. 8 hydrogens. And these are all, this is grams per mole. I'm just not writing that in there. Save space. So that takes care of the nitrogen, the hydrogen, and that chromium. Chromium, we only have 1. And I have to go to the periodic table for me anyway. 51, 52, 52.00, rounded off. I always round off 2 decimal places. And then 4 oxygens. And oxygen is 16. Okay? And then this is all times 100. After you've done this calculation, then multiply it by 100. And if I did it right, it should be 18.4%. Okay? In the interest of time, I'm not going to go through the whole calculation. I heard another ding. Christy. Let me see. Desiree and Zoe. See if they snuck in while I was at the board. Desiree. And no. Okay. All right. So we'll go to the next one. Number 30. Okay. Now, I hope what you're doing is you're taking that review document, and for each of these types that we're coming up with, you're working as many of them as you can of that type. The practice repetition is reinforcing of the method. And then hopefully you'll get bored doing them. If you get bored, that means you know what you're doing. 30, a hydrocarbon, which is hydrocarbon. Hydrocarbon. Hydrocarbons have only carbon, only hydrogen. Is found to be 85.6% carbon. Right, in carbon. So how much is it in hydrogen? Because it doesn't say. Well, if there's only this and that, then it's 100 minus that, isn't it? Which would be what? 4% hydrogen. There we go. I think I put those a little too close together because we're going to need to calculate some things. 14.4% hydrogen. Okay, what's the question? What's the empirical formula for this compound? So we don't have to go all the way to the molecular formula. In fact, we can't because there's not enough information. What are we missing? If we wanted to go all the way to the molecular formula, we need the molar mass of the actual compound. Right? We don't have that. We've got just enough information to go to the empirical formula, right? The simplest whole number ratio of elements in the compound. So remember how we do that? This is all we've got, right? Not yet, right? You can't do anything with percent because percent is parts per hundred. Right? So what we have to assume is, for the interest of calculation, just assume your sample is 100 grams. Okay. And if it's 100 grams, parts per hundred by mass is 85.6 grams per 100 grams. So that means in that much compound, we have 85.6 grams of carbon and 14.4 grams of hydrogen. Now we can do something with it. And when we have an empirical formula or a formula of any kind, the ratio is atoms per atoms per atoms per atoms, not mass, right? We've got to find out how many moles of carbon and how many moles of hydrogen that represents in order to put it in the form of a formula. So now we want to convert to moles. Oops, shift that over a little bit. 12.01 grams per mole. Right? That cancels the grams and leaves us. This tells us how many moles of carbon that is. And this will tell us how many moles of hydrogen there are. Right? So I will have to do this calculation to continue. So 85.6 grams divided by 12.01 is 7.127 moles of carbon. Now what we're doing is we're establishing, this gives us the mass ratio of the two. Right? And that's going to be consistent for any of if that compound, no matter what its source, remember? The law of definite proportions. This is the proportion by mass. But we can't write the formula until we know the moles, the numbers of atoms. And the ratio here, we're just converting this ratio to this ratio of moles. So if I get 14.4 and divide by 1.01, I get 1.426 moles of hydrogen. Now we do what you wanted to do. Okay. Now you divide by the smallest one, because we've got to get rid of fractions, right? These formulas don't look right unless they're whole numbers, because if they can represent atoms to atoms, you can't have a fraction of an atom. You could have a fraction of a mole, but not a fraction of an atom. So in order to be consistent between atoms in a formula and moles in a formula, we need to have whole numbers. So we're going to divide through by that value, both of them. Right, this is obviously 1. And let's see. Okay, I just get my divide key. And this is rounded off 0.5. Okay, we still got a fraction here. Now, how do we get rid of that fraction? By 2, yeah. Think of it this way, 1 times 2. If you multiply by 2, 2's cancel and you're left with 1. So if we say times 2 times 2, this gives us 2 here, that gives us 1 there. So our empirical formula is... Yep, go ahead.
I got 4.99 instead of point.
Wait a minute, did I read that wrong? I get 0.499. Hold on a second, let me do it again. You're probably right. I skipped a step. And I trusted my calculator, which is a mistake. 7.127. 1.426. Yep, sure. Closest whole number here is 5. That's 1. Okay. So that puts 5 here and 1 there. That's not what it says. Okay. Let me see what I did wrong. 85.6%, 14 forms, that's right. So we go to 100 grams.
Okay, 14.4 divided by 1.01 should be 14.26.
Exactly right. In which case, we're not dividing by that one anymore, are we? If that's 14, we're going to divide by 7.127. That's 1. 7.127. See, I read my calculator wrong. Put the decimal in the wrong place. So 7 that's about 2, isn't it? Yeah. So it should be 1 to 2. Well, you don't have to write that in there. CH2B. Okay. I'd like to be able to say that was planned, but I just made a mistake. All right, that was 30. Let's see, 32. The empirical formula of styrene is CH. Okay. We're given that. And its molar mass is 104.1. 104.1 grams per mole. This is the molar mass, and I abbreviate that molecular weight. It's old school. And the question is, what's the molecular formula for styrene? We know this one. Remember, what we need is what's the multiplier? If this is the simplest whole number ratio, the actual whole number ratio is multiplied by a factor. And if it's 1, you get a certain value. If it's 2, you get another value. If it's 3, you get another value. And see which one comes closest to that value. But the way to find X easier than that is you take this value and divide by what I call the empirical weight. The empirical weight is whatever this says, 1 carbon and 1 hydrogen. And so that's 13.02. Right here. Divide 13.02 into 104. And I get about 8. Rounded off to the next whole number. So if X is equal to 8, then the formula is C8H8. Okay? All right. It's 32. We got another one. 30. Adipic acid contains carbon, oxygen, hydrogen, percent by mass. What's the empirical formula? Do we need to go through this one? Right? I can get you started. If we know it's got carbon, hydrogen, and oxygen only, then we have, I'm going to write it this way. 49.
It's the same way as number 30.
Oh, no, they're not related because this one has oxygen in it. Right, number 30 had only carbon and hydrogen, correct?
Yes.
Yeah, no, we can't relate them that way. We have to do it the hard way. So this is carbon. Usually it's written, notice the answers, it's written carbon, hydrogen, oxygen. So I would write hydrogen next, 6.85. Hydrogen. And 43.84% oxygen. So if we assume that does it tell us a weight? No. So if we assume a 100 gram sample, then we have 49.32 grams of carbon, we have 6.85 grams of hydrogen, 43.84 grams of oxygen. Now we just need to convert to moles. grams on the bottom, moles on the top. Okay. So for carbon, we know that's 12.01, right? We know hydrogen is 1.01 gram per mole, and oxygen is 16. Nice. I'm already halfway there. I might as well go ahead and do it. 4932. See if I can get it right this time. Okay, 4.107. 4.107 moles. And that's a 100 gram sample. 6.85, 1.01. I get 6.782 moles. This is carbon, hydrogen. And 43.84 divided by 16 is 2.70 moles of oxygen. Now we can just divide through by the smallest one, 2.740, 2.740, and 2.740. So let's see, this is going to be 1, of course. Let's see, let me flip that one. This is about 2.5. And I better do this one. 2.740. This is about 1.5. Okay. So now we just need to get rid of the fraction. The ratio is established. Moles, moles, moles. We need to get a whole number. So if we multiply everything through by 2, the ratio will still be the same, but we'll have whole numbers now. 2 there, 5 there, and 3 there. So we have C3H5O2. Okay. That's the empirical formula for adipic acid. Right. How about vitamin C contains elements carbon, hydrogen, oxygen, known to contain 40.9% carbon, 40.58% hydrogen by mass. The molar mass of vitamin C has been found to be 180 grams per mole. The molecular formula. All right, so this one they want us to go all the way to the end for vitamin C. 34. Okay. So we know there's 40.9% carbon, 40.9% carbon, 4.58% hydrogen, and what's left over is oxygen. Let's see, somebody, Desiree. Or, let's see, did I miss Zoe in there somewhere? No, she's not here. Hope she's okay. Okay, did you calculate what's oxygen?
54.52.
54.52. So add these up, and it should be 100%, or very close to it. So we're going to assume 100 grams again, so that we can get that many grams of carbon, this many grams of hydrogen, and this many grams of oxygen. Now we just need to convert to moles. Right? It's time to get bored. Same way again and again and again. So this is oxygen at 16. This is hydrogen at 1.01. And this is carbon at 12.01. 3.9, 12.01, 3.405, and 4.58 divided by 1.1, 4.53, 5, and 54.52 divided by 16. It's 3.408. Okay. So if we divide through by 3.405, which is the smallest one, this one is about 1. Right, it's very close. It's close enough. This one is exactly 1. And this one divided by 3.405 is 1.333. So this is like 1 1/3. So how do we get rid of the third? We multiply it by 3. And so if we multiply everything by 3, that gives us 3 here. 3 times 1/3 is 1, plus 3 is 4. And then this is 3. Okay, so that's the empirical formula. We have carbon. It asks for the molecular formula, didn't it? Okay. Empirical formula is 3 carbons, 4 hydrogens, and 3 oxygens. And we need to find out what that X is. So what we need is the empirical mass of this formula, right? 3 times 1201, which is 36.03. Plus 4.04 for the hydrogens, plus 3 times 16 is 48, right? So that's 7, 0, 12, 18, 1, 7, 8, 88.07. I did my calculations right. 88.07 is the empirical weight. And we're given 180 grams per mole is the molecular weight. So the molecular weight divided by the empirical weight is 180. I think they should put a decimal there. Divided by 88.07. And I get approximately 2. And so if X equals 2, then the molecular formula should be C6H8O6. Six. 686. Okay. That was 34. 36. Starting to get weak on me. 36. How many of the following are true concerning balanced chemical equations? All right. 1, 2, 3, 4, and 5. All right, is 1 true? The number of molecules is conserved. True or false? No. You can have a different number of molecules because when you balance the equation, you're changing the coefficients. And that coefficient establishes the number of molecules. Right? The number of molecules doesn't have to be the same on both sides. In fact, look at this one. Hydrogen gas plus oxygen gas yields water. Right? If we balance this one, of course, it's going to be 2 over here and 2 over here. So this has 1, 2, 3 molecules on that side and 2 on that side. But the equation is balanced. That's just an example to show you that this one is false. How about the coefficients for the for the reactants tell you how much of each reactant you are given. What they mean by how much is mass. Right? And that doesn't tell you, coefficients don't tell you that. They tell you how many molecules of each one there is. Atoms are neither created nor destroyed. Yeah, that's always been true. The coefficients indicate the mass ratios. Nope. We just counted that one out with this one. The sum of the coefficients on the reactant side equals the sum on the product side. So, not necessarily. So the only one that's true is that one right there. A would be 1. There's only one of them that's true.
I know there's only one. I would have picked 3 just because know 3.
Oh, yeah.
But yeah.
Yeah, stop and think.
I don't follow the question all the way through.
Let's see, that was 36. 37. I think I'm going to have to switch markers. Different color. I don't know if that'll show up good on the. Appears to be. In balancing an equation, we change the blank to make the number of atoms on each side of the equation balance. Right? This is just memorization. What do we have to change? Once we get the elements, compounds, whatever the case may be for reactants and products written correctly, can't touch the subscripts. The only way you can balance it is with coefficients. So B has to be the answer there. That's the only way. Is that showing up? Is that color showing up okay for you guys? Yes, no, maybe. Maybe I better go back to black. Because I know black shows up.
I see it fine.
Okay. See, I need to turn my sound up, don't I? There we go. 39 and 40. Can I squeeze those in there? Yeah. What's the coefficient for oxygen when the following equation is balanced? So we've got ammonia, gas, plus oxygen, gas. Notice I left a place here for coefficient if I need one. Nitrogen dioxide, gas, and water, gas. So this is taking place at either such a low pressure or a high temperature that water is a gas. All right, so how are we going to balance this? Budget method. We've got nitrogen, hydrogen, and oxygen. All right, we're going to save that one till last. But first we need to count. 1 nitrogen, 3 hydrogens, 2 oxygens. 1 nitrogen, hydrogen, 2 hydrogens, and 3 oxygens. Okay. So if we're gonna save the oxygen till last, our only option is hydrogen first. So let's see. We need how are we going to do that? Hydrogen, 3 hydrogens here, 2 there. Okay. This is one of those tricks that we hadn't gone over yet. When you've got an element in one place on one side and one place on the other, this works. If they're in 2 different places on one side, then you have trouble doing it. But in this case, we've got 3 here and 2 there, just cross multiply. So bring that 2 over here, bring that 3 over here, and then recalculate. So now we have 2 nitrogens. We have 6 hydrogens. And here we have, still have 1 nitrogen, but let's see, 6 hydrogens. And oxygens, now we have 3 plus 2 is 5, correct? 3 plus 2 is 5. 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 3 plus 2 is Did I count that right? Let's see. 2 plus 6 is 8, 9, 10. 6, 7, 8, 9, 10. Yep. 1, 2, 3. 6 is 9, 10. Nope, that's not right. 1, 6, 11, 12. I need 12 here. So that's 3 plus 6 is 9, plus 1 is 10. So there's something wrong here. I need to recount. 3 plus 2 is 5, 6. Well, it says it's right. 1, 2, 3, 9, 10. That says 12. Am I counting wrong? 1 nitrogen. Is it 6 hydrogens? Yeah, 6 hydrogens. 3 oxygens plus 2 oxygens is 5. 1 nitrogen. So that should add up to the right amount. It's 3 and 6. Oh, it's right. It's right. Yeah. So this is 3 times 3 is 9, 10, 11, 12. Okay, we're good. Now we've got hydrogen balanced. We want to get nitrogen balanced. So we need a 2 here. And that changes the number of oxygens. So 3 oxygens plus 4 oxygens is 7. Okay. Now we can deal with the oxygens on this side. We need 7 oxygens. So here comes another trick. How do you get 7 oxygens out of an even number? The only way you can do it is with a fraction. So if we say 7 halves, that gives us 7. Correct? Think of it this way. Oxygen molecule. Right? That's one of these. If we say 7 times that, 1, 2, 3, 4, 5, 6, 7. Right? That's 7, but we only need half that many. So we just cross out half of them. Now we have 7.
So for the coefficient, it's okay to use the decimal point? Like, or
Use a fraction.
yeah.
This is an intermediate step. We're not finished yet. Right? That's in that helpful hints document on balancing equations. It's one of the methods. Now that we have officially, right, it's balanced, but we don't want fractions. So here's how you get rid of the fraction. These ratios now are established. 2, 7 halves, 2, and 3. That establishes the ratios of the coefficients correctly for a balanced equation. But we want to get rid of the fraction. So if we do the same thing to both sides, do the same thing to every one of these, their coefficients, then we still have the same ratio. So what we're going to do is multiply the entire equation through by 2. Okay. That gives us 4 here, gets rid of that 2, gives us 4 there, and 6 here. But we used up that one. So the ratio is still the same, but now we have whole numbers. 4, 7, 4, and 6. So what's the sum of the coefficients? Well, 4 plus 7 is 11, plus 4 is 15, plus 6 is 21. Oh, wait a minute. I'm looking at 40. 39. What's the coefficient of oxygen? Oxygen is 7. Okay. Did I lose anybody with that trick? It's kind of like incorporating mathematics into our chemistry, right? Because you know that if you have an equation in math, if you do the same thing to both sides, if you multiply both sides by the same value, right, it's the same equation. All right, 40. What's the sum of the coefficients for the following equation when it's balanced with the smallest whole numbers? All right, here we have sodium azide plus sodium nitrate. See, let me make spree. This over here like that. And sodium, no, this is sodium azide, excuse me. This is sodium amide. And then sodium hydroxide. We got sodiums all over the place here. And then ammonia. Okay, this one's going to be a little more difficult. So we definitely need to use the budget for this one. Sodium, nitrogen, hydrogen, and oxygen. Sodium, nitrogen, hydrogen, oxygen. That's everybody. Okay, on this side we have two sodiums. We have two nitrogens, two hydrogens, and three oxygens. So that's six, that's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. Sodium on this side is 2. Nitrogen is 3, 4. Okay. Hydrogen. 1 plus 3 is 4. And oxygen is 1. So that's 8, 9, 10, 11. 3, 4, 5, 6, 7, 8, 9, 10, 11. So the initial count is right. Smudge that one. Okay, now the question is where to start. Well, sodiums are already good. Nitrogens maybe, hydrogens maybe, oxygens maybe. Here, 3 here. That gives us, let's see. That gives us 3 oxygens and 6 hydrogens. And this 3 gives us 4 sodiums, 1 plus 3, 4 nitrogens, 6 hydrogens, and we still have 3. That's it. Oh, that was a lot easier than the first way I tried to do it. All right, so the sum of the coefficients is, and don't forget these are ones. 3, 4, 5, 8, 9. I don't know if the questions about this would do any good, right? It's just, I was chasing a rabbit down the wrong hole. Let's just put it that way. Right. The easiest way to do it is to use two coefficients at the same time. If we try to do, say, this one and then say, all right, what can I do on this side? We have to do 2 at the same time in order for that to work. All right. And just ate up 15 minutes. 43. When the equation, blah, 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 is balanced with a small set of integers, the sum of the coefficients. So we got another one here. All right, this one's going to be better behaved. No. H10, 14, excuse me, 14. This is a hydrocarbon. And oxygen. Whenever you burn a hydrocarbon in oxygen, you always get carbon dioxide and water if the reaction is complete. Right? You don't have any incomplete combustion like the internal combustion engine does. But a complete combustion will give you those factors. What you're going to find out is for this type of reaction, hydrocarbon plus oxygen, you're always going to have to use the fraction trick. Carbon, hydrogen, oxygen. We have 6 carbons, 14 hydrogens, and 2 oxygens. We have 1 carbon, 2 hydrogens, and 3 oxygens. Okay. I'm just going to start with the carbons. We need 6 of them here. That makes it 6. That's 12, 13 oxygens.
Jojo, get Loki.
Question? Hydrogens now, because we're going to save the oxygen till last.
No.
Let's
Put them out if you have to.
Question? All right, where was it? So we got 14 hydrogens. Now we have 7 plus 7 oxygens plus 12 is 19, right? 19 oxygens. So now we can use the fraction trick, right? We need 19 oxygens. 19 halves will give us 19 oxygens. So now we're going to multiply through by 2 and get rid of that fraction. So now we have a 2 here, a 19 there, a 12 here, and a 14 there. So the sum of the coefficients, that's 2 plus 19 is 21, and that's 26, so that's 47. Right, B. There's only one hydrocarbon that doesn't use the fraction trick that I know of, and that's methane.
So like any formula that is just CH, that's the hydrocarbon. And all of that's gonna have to be fresh.
If it's burned in oxygen, if it's a combustion reaction. Yeah. You combust it in oxygen, gives you, now, I probably shouldn't emphasize that one too hard because there are carbon hydrogen compounds that are not these my mind's going blank. You can have other types, like acetylene is this, right? And it may not need a fraction.
The only whenever it's mixing oxygen.
Well, when it has to be burned in oxygen, of course. But these, shoot, why can't I think of the name? That's going to bug me until I remember it. It'll happen when I'm not thinking about it. Let's go on. Reaction occurs between sodium carbonate and hydrochloric acid. So you have to write sodium carbonate. Carbonate's a 2 minus charge. It's the 1 plus, so you need 2 of those. And hydrochloric acid, HCl, and produces sodium chloride plus carbon dioxide and water. So he gave you the names of the compounds. In order to balance the equation, you've got to be able to write the compound. If you can't write the compound, then you might as well just go to the next question. All right, so we're going to balance these. We might be able to balance these pretty easy. I'm going to try it without the budget method. You need 2 sodiums. Right? Now you need 2 chlorines. Right? Now you need 2 hydrogens. Well, we got 2 hydrogens. Let's see, how many carbons do we have? 1 carbon, 1 carbon. Oxygens, we have 3. 1, 2, 3. That was balanced. 12211. D. Now, if you're more comfortable with the budget method, you can do that, right? But some of these equations are very well behaved.
So in this exam, we should be able to name all the compounds.
You should be able to write the compound formula from the name, right? That was chapter 1 and 2. Actually, chapter 2. That's where we learned how to do that. Chemical reaction has equations 2A plus B yields C. Two A plus B yields C. Which of the following figures best illustrates the stoichiometric ratio of A and D? Stoichiometric ratio is exactly 2 for every 1 B. And then you only produce 1 C from that. So let's look at each one. Roman numeral 1. How many A's do we have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4 B's. Right. So you have 8 to 4. That's a stoichiometric ratio. How about 2? A's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Nope. That's a 1-to-1 ratio. We need a 2-to-1. Roman numeral 3 is the other way around, right? It's 8 to 4. And the last one, A's 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, 8 B's. No, last one can't be it either. And it has C's in it also. Stoichiometric ratio. The point here is that the ratio is before the reaction occurs. What is the ratio? The ratio is exactly 2 A's for every 1 B, and that A is the only one that's satisfied. I mean, Roman numeral 1, which is A, 1 only. All right. 46. Looks like I'm going to be here for a while after you guys are gone. 7.11 gram sample of potassium chlorate was decomposed according to the following equation. How many moles of oxygen are formed? Right, so we're given the balanced equation. Potassium chlorate is decomposed. All you have to do is heat it up a little bit. 2 KCl plus O2, 3O2. Okay, we're starting off with 7.11 grams of potassium chlorate. Right? And we want to know the moles of oxygen. Okay. So what's the #1 rule in stoichiometry? You can't go anywhere without moles. If you don't have moles, you're stuck. So we're going to convert this into moles, which means we got to get rid of the grams and leave us with moles, right? The quotient ratio of grams and moles always means molar mass. So what's the molar mass of KClO3? Let's see, potassium is 39.10 grams per mole. Chlorine is 35.45. I had that memorized. It's right up there. And 3 oxygens, 3 times 16 is 48. All right, so we add those together. And let's see, this is 22. Carry the 2. Let's see, 6, 10, 12. 122.55. That's how many moles of potassium chlorate we are decomposing. So that's 5.80. Okay. times 10 to the minus 2 moles of potassium chlorate. But we want to convert it to moles of oxygen. So how do we do that? Well, potassium chlorate ratioed with oxygen is 3 to 2. Okay? So we just multiply by 3 and divide by 2. And I get 8.70 times 10 to the minus 2 moles of oxygen. Oh, they have standard notation. So let's move the decimal to the left 2 places. 1, 2, 0.0870. D. Okay? That's a very, very simple stoichiometry problem. $47. Scroll that one a little bit. There we go. How many grams of calcium nitrate can be produced by reacting excess HNO3, nitric acid, with 6.33 grams of calcium hydroxide? So the product is calcium nitrate. We're going to react calcium hydroxide. Right? Is that right? That's a -1 polyatomic ion. That's an alkaline earth +2. So we need 2 of these. Plus HNO3 in excess. Excess. And that's going to yield what? Well, one of the products is calcium hydroxide. What else? Remember when you react a base with an acid? Oh, excuse me. My mistake. Nitrate. There's something that looks funny with that one. We're taking this nitrate and replacing the hydroxides with it. So what's left over? Remember, an acid plus a base yields a salt plus water. Without that water, you can't balance the equation. Acid-base reactions are very well behaved, most of them, for balancing. All right, so if we have 1 water over there, but we have 2 hydroxyls here, we need 2 hydrogens here. And that gives us 2 there. Now see if I'm right. 1 calcium, let's see, 2 oxygens plus 6 is 8 oxygens, so that's 6 plus 2 is 8. And hydrogens, 2 hydrogens here, 2 hydrogens there is 4 hydrogens. So we're balanced. Okay, now we can go to the question. 6.33 grams of calcium hydroxide does what? How many grams of calcium nitrate? So we want mass of calcium nitrate. We still have to convert to moles. That's the only way we can go anywhere. So we need the molar mass of calcium hydroxide. Right? What's calcium? It's 40, isn't it? 40.08. For the calcium. And we have 2 oxygens, which is 32. And we have 2 hydrogens, which is 2.02. Right? 1, 4, 7, 74.10. 4.10 divided into 6.33 is 8.54 times 10 to the minus 2 moles of calcium hydroxide. But we need to convert that to moles of calcium nitrate. So the ratio is 1:1. Right? 1:1. That means we have exactly the same amount in moles of the calcium nitrate. So we just need to convert that to grams. Grams per mole, molar mass. So let's see, calcium nitrate will be 1 calcium, 2 nitrogens. Right? 2 times 14.01. It's 2 nitrogens and 6 oxygens. 16. Okay. So let's see what we get. 40.08 and then 28.02 for the nitrogens and 16 here, 96 for the oxygens. And that's 164.10. Okay, times this value right here. So I get 14.3 significant figures, 14.0 grams of calcium nitrate. Okay. We didn't have to worry about limiting reactant because we were told a certain amount of calcium hydroxide and excess nitric acid. So the nitric acid never ran out. Right. We knew that calcium hydroxide was actually the limiting reactant. All right. Am I ever going to get out of chapter 3? I don't know. Got 5 minutes. Okay, for this reaction, P4O10 plus water yields H3PO4, which is phosphoric acid. What mass of P4O10 must be consumed if 3.71 times 10 to the 23rd molecules of water are also consumed? All right, so let's write the controlling reaction. O10, and this is a solid. And 6 waters. They've already balanced the equation for us. Isn't that nice? And then 4 H3PO4 aqueous. Okay. 3.7. This is the amount of water that's consumed. We want to know the mass of this one. But we know 3.71 times 10 to the 23rd molecules of water have been consumed. And we want to get at this mass. So first thing we have to do is convert to mole, because this is a mole ratio. Well, you know, we could do it 2 different ways. We could convert this to moles and then use 6:1 as our conversion factor. Right, that works. Or we could use 6:1 on the molecules and then convert to moles. Either way works. Which way do you want to do it? You want to do moles first? Okay. All right, so 1 mole is 6.022 times 10 to the 23rd molecules. Right. That tells us how many moles of water have been consumed. 3.71 exponent 23 and 6.022 exponent 23. So that's 0.616 moles of water. And now we need to convert moles of water to moles of P4O10. And the ratio is 6 here, 1 there. So we need to divide that by 6. And that's 0.1027 moles of P4O10. So now we need to convert it to mass. Moles on the bottom, grams on top. So what's the molar mass of that compound? Well, let's see, 4 times phosphorus, 30.97. And 10 times oxygen, which is 16. So that's 160 here. And then 30.97 here to the 4. And add those together, I get 283.88 grams per mole. 283.88 times 0.1027. And I get, let's see, standard notation, yeah. So I get 29.2 grams of P4O10. Okay, what's the best answer? B is the closest one to mine. I think that's some rounding error, and I didn't round things in my calculator, so that's the difference. Now it's 52. Okay. Yeah, it's 1:45, so if you have to go, I'll just keep going and post the video later. There's 58. Okay, 5.95 gram sample of silver nitrate is reacted with barium chloride according to this equation. To give 3.17 grams of silver chloride, what's the percent yield of silver chloride? All right, so how do we calculate percent yield? We have to know the theoretical amount, the stoichiometric amount, and then we have to know the actual amount recovered. Okay, it's given 3.17 grams of silver chloride were actually recovered. But we're only given 5.95 grams of silver nitrate. We've got to find out how much silver chloride that represents if 100% conversion takes place. That's the scheme. So we got silver nitrate and barium chloride yields 2 silver chloride. Yep. And I'm leaving out the phases in the interest of space. Let's see, that's 2. There we go. Okay. Okay. So we're given 5.95 grams here. 5.95 grams. What we want to know is what's the mass here with 100% conversion. So we got to convert that to moles. We need molar mass. Okay, silver nitrate. Silver, 107.87. Nitrogen, 14.01. Oxygen, 3 times 16, 48. Let's add those up. 107.87, 14.01, and 48. This is 169.88. Divide that into 5.95, and we get 3.502 times 10 to the minus 2 moles of silver nitrate would be consumed 100% to yield how much silver chloride? Well, notice, for every 2 of those, you get 2 of those. It's 1 to 1. We don't even have to do this. This is 3.502 times 10 to the minus 2 moles of silver chloride. So all we have to do is convert that now. Oops, the mass. Silver chloride. Well, here's the silver. What's the chloride? 35.45. Let's see. I think I hit a wrong key. Let me try that again. All right, this is 143.32. Okay, so that times 43.32 times 3.502 exponent side times. That's 5.02. That would be 100% efficiency. But we only got 3.17 grams. And we were expecting 5.02 grams times 100. So there's your percent yield. And I get 63.2. All right. The best answer there is D, 63.1. All right, that was 58. What's next? 59. Okay. Consider the following reaction. CH4 gas is methane plus chlorine gas yields carbon tetrachloride plus 4 hydrogen chloride gas. What mass of carbon tetrachloride will be formed if 1.20 moles of methane react with 1.11 moles of chlorine? All right, so we need our equation, CH4 plus 4 chlorine gas yields carbon tetrachloride plus hydrogen chloride. Okay, 4141. Okay, so we're given absolute amounts of 2 reactants. You can be pretty sure that one of them is going to run out first. So we got to find out which one's the limiting one. That will be the jumping off point for determining how much of the carbon tetrachloride will form. Okay, 1.20 moles, 1.20 moles. And chlorine is 1.11 moles. All right. So there are a couple of ways you can do this. You know that for every one of these, you need 4 of those. Right. So you need a whole lot more of this than that. This is going to run out first. And you could just take this one and run with it. Or we could be methodical and say, all right, what if we use all of this to make that? How many moles of that would it produce? So we need the ratio of chlorine to carbon tetrachloride, right, which is 1 and 4. And so 4 divided into 1.11 is 0.2775 moles of carbon tetrachloride. Or we could do this one, 1.20 moles. And the ratio here is 1 to 1. Right, so we're going to have 1.20 moles. Right, now we can see plainly that this one produces the least amount, which means this one is limiting. That's how many moles of carbon tetrachloride you can produce with this mixture. So the question is, what's the mass of this one? Now we just need to convert that number of moles, 775 moles of carbon tetrachloride, into mass. Okay, so we need the molar mass of carbon tetrachloride, 12.01 for one carbon, and 4 times 35.45 for the chlorines. And 12.01 added to that is 153.81. And let's see, I got them both in here right next to each other, just times. We have 42.3 significant figures, 42.7 grams of carbon tetrachloride. That's D. Okay. This was an exercise in limiting reactants. All right. My goodness, I'm still in chapter 3 with 61. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? So if we have 2 C2H6, which is, let's see, I think ethane, that's ethane, plus 7 oxygens yields 6 water plus 4 carbon dioxide. Okay. If we have equal masses of C2H6 and O2, there's no limiting reactant. Equal masses of this one and that one. Well, what we need to do to solve this one is, what's the molar mass of each one? Right, because the ratio is 7 to 2. So we'd have 7 oxygens for every 2 C2H6. Okay, so the molar mass for oxygen is 32. And the molar mass for C2H6 is, let's see, 2 times 12.01 and 6 times 1.01. So let's see, that's 24.02 and 6.06. That's 30.08. This is 30.08 grams per mole. But this ratio says that I need 7 times that to be stoichiometric. That's what they mean. No limiting reactant means stoichiometric ratio. So 7 times this is much greater than that. So equal masses of the, let's see, equal masses, the oxygen would run out first. So A is false. Can't be. If we have an equal number of molecules of C2H6 and O2, there's no limiting reactant. An equal number of molecules means the ratio, though, is 2 to 7. Right? Equal numbers would be 2 to 2 or 7 to 7, something like that. So this one can't be true either, because for every 2 of these, you need 7 of those. Right? How about C? If we have more mass of C2H6 than O2, then O2 must be limiting. If we have more mass of this one, right? The mass ratio of these two would be 2 times that one would be 60.16 grams. Ratio to 32, enter 7 times, would be 224 grams. So this is the mass ratio of the two. If they're exactly that amount, then it's stoichiometric. But C says if we have more mass of C2H6, this one, we have more mass of this one, then, that should be than, not then. If we have more mass of C2H6, then O2 must be limiting. All right, what that means is if this mass is greater than that one, then yes, this one would run out first. Because this would have plenty, it have a lot more than you need. Right, over 224 here, there'd be plenty. That's a lot more than 60. So oxygen would run out first. C is true. Right. E says none of the statements are true. We did find one that's true. And we don't have one that says two of the above are true, so we don't even have to look at D. We know that C is the true one. That one was a bit more difficult than the usuals. 62. Equal masses in grams of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Right. For this one, you need your balanced equation. Hydrogen gas plus oxygen gas yields water, and you have to balance it. Right? So we need 2 oxygens. Now we need 4 hydrogens. That's balanced. Okay. Equal masses. So if you have X grams here and you have the same amount here, well, what's the mass of this one? Right, it'd be 4.04 grams ratio to 16. Oops, sorry. 2 times 16, 32 grams of oxygen ratio to this much hydrogen. How did I get that? Well, how many atoms of hydrogen do we have? We have 4, or 4 moles, actually. 4 moles of hydrogen. So 4 times 1.01 is 4, 4.04. And 2 oxygens is 32. So this is the mass ratio of the 2. What it's saying is equal masses in grams of hydrogen and oxygen. We have equal masses here. Right? Say we have 32 grams of oxygen and 32 grams of hydrogen. We got plenty of hydrogen, a lot more than you need. So oxygen would run out. Oxygen gas is limiting. That one is the limiting one. So to solve this type of problem and the one before, it's instructive to look at the mass ratio that comes from the balanced equation. Then these statements make sense. 64. Hold on a second. Let me see where I am in the review document. You know what? We have been in chapter 4 for quite some time. When did it go to chapter 4? No, we haven't. We're still in chapter 3. We're still in chapter 3. For the reaction, nitrogen plus hydrogen yields N2H4, or hydrazine. If the percent yield for this reaction is 82%, percent yield, put that up here, is 82.0%. Okay. What's the actual mass of hydrazine produced when 25.57 grams of nitrogen? Okay, so what we need is the balanced equation plus, oops, put them in the same order. N2 plus hydrogen yields N2H4. Okay, that's balanced. We're given 25.57 grams of nitrogen. 25.57 grams of nitrogen. 4.45 grams of hydrogen. Okay, and we want to know how much hydrogen, of hydrogen is produced? In grams, actual mass. Okay, so what we need first is the theoretical 100% value. Then we can apply the yield to it. So we need molar mass here, right? 25.57 grams of nitrogen converted to that 14.01 times 2 is 28.02. Right? So we divide that one into 2557. 28.02 divide, and I get 0.9126 moles of nitrogen. How about hydrogen? 4.45 grams. We want to convert that one to moles. And that's hydrogen here, right, is 2.02 grams per mole. So 4.45 enter 2.02 divide is 2.203 moles of hydrogen. Okay. Now, you can look at these two together and see which one runs out first based upon the ratio of 1 to 2. Or we can go ahead and just calculate how much hydrogen would be produced if all of each one was converted. So the ratio here and the ratio here to this one and this one, that's 1 and that's 1. And this is 1 and that's 2. So this is actually going to be 0.9126 moles of hydrogen. And this one's going to be half of that. 1.101. 1.101. And you can see from this calculation that this is the limiting one. Nitrogen runs out first. And this gives us moles of hydrogen that now we can convert to grams of hydrogen. We just need the molar mass of hydrogen, which is what? 2 times 14.01, 4 times 1.01 for the hydrogen. So a quick calculation is 3206 grams per mole times 0.9. Let's see, 0.126 times, and that's the theoretical yield is 29.26 grams of hydrogen. All right? But it's only 82% efficient. So how do we get the actual amount? Well, remember the calculation, right? Percent yield is equal to actual minus theoretical times 100. Okay. So if we rearrange that, find out what the actual amount is. Actual equals theoretical times percent yield times 100. Or you can just use the fractional amount. Excuse me, not times. Divided by. Numerator on this side, denominator on this side. So the theoretical yield is 29.26. Percent yield is 82, and divide by 100. So we get 23.99. 23.99 grams. Or the nearest one, right? Rounded off to 24. Yeah, rounded off to 24. All right. Let's see, are we ever going to get to chapter 4? What's the molar mass of tetraphosphorus decaoxide? This is an easy one. Right. Type 3 compound, right? 2 nonmetals, tetraphosphorus decaoxide. Actually, we did that one earlier. It was for a different problem. So we need phosphorus, which is 30.97 times 4, and then 10 times 16 for the oxygen. Right. And if I do it right, it should be 284 grams per mole, just in the interest of time. My goodness, is this ever going to end? 69. Which of the following samples contains the greatest number of moles of carbon atoms? All right. This is where Henry Ford comes in. A, B, C, D, E all contain the same numbers. All right, so we'll have to look at all of them to find out. If they don't all contain, then we can throw E out. 58 grams of C4H10, 46 grams of C2H5OH, 44 grams of CO2, and 180 grams of C6H12O6, glucose. Okay. Greatest number of molecules of carbon atoms, moles of carbon atoms. Okay. So what we need to do first is find out how many moles of the compound there are. Right? We need a molar mass for C4H10. So carbon, 12.01, 4 times. Is 4804 plus 10 hydrogens, 10.10. I did that one in my head. 5814. 5814. So while I got it in my calculator, let's do that calculation. 58 divide. So this is 0.998 moles of the compound. Right? That's the first step. Then we need C2H5OH. So 2 carbons, 6 hydrogens, and 1 oxygen is 3407. So I divide that into 46, and I get 1.35 moles of compound. Okay. Carbon dioxide, 12.01 plus 32 for oxygen, 4401. Well, that's 1 mole of compound. Right? And 12.01 times 6, and then 12.12 for the hydrogens, and 6 times 16. Add that. 180.18. Well, that's 1 mole compound. Okay, that's the amount of compound. What we want to know is number of moles of carbon atoms. So the ratio here from compound to carbon atoms is the same ratio as moles. So we really don't have to go to carbon atoms. We can stop at moles and make the comparison. Okay, what's the ratio here? Well, 4 for every one. 4 carbons for every one compound. 2 for every one here. 1 for every one here. And 6 for every one there. So this is going to be 6 moles of carbon. This is going to be 1 mole of carbon. This is going to be 2 times 1.35, which is 2.7 moles of carbon, and 4 times 0.998, 4 times, well, it's about 4. For comparison purposes, this one, D, D has the most carbon atoms of those that we were given. And E, of course, is false, because they don't all contain the same amount. All right, that was 70. Oops. 71. Yeah, 71. All right. Naturally occurring iron contains percent of one isotope, percent of the second, percent of the third, percent of the fourth. These are all percentages by numbers of each of these isotopes. And the respective masses are given for each one. Calculate the average atomic mass of iron. So you remember how to do that. Use the fractional equivalent of the percent. So 54, right? They're given in order. Okay, 53.90. 53.940. These are all atomic mass units. And the contribution that this one gives is 5.82%. Right? 0.0582. Right? And how do I know that? If you multiply that by 100, go 1, 2, 5.82. Okay. Second one is 55.935. 55.935 times 91.66%. Okay. The fourth one, 56.935. If I read those right. Yeah. 2.19%. And the last one is 57.933. And its abundance is 0.33%. That's right. Okay, what you do is multiply each one of these out and then add them together. And you should get 55.85 atomic mass units. All right, so I just set the problem up. You can do the crunch the numbers. All right. Okay, let's see here. Cyanocobalamin, vitamin B12. Concentrated in animal tissue, but not in higher plants. People who abstain completely from animal products may develop anemia. That is true. So cyanocobalamin is used in vitamin supplements. Contains 4.35% cobalt by mass. What's the molar mass of cyanocobalamin, assuming there is 1 cobalt per molecule? All right. Let me refresh my memory. All right, let's see. What did it tell us? 4.35% cobalt. B12 is 4.35% cobalt by mass. All right, what's the molar mass of cyanocobalt? So if we want molar mass, we're going to need grams per mole. We've got to have grams per mole in order to do this. This is percent. So what we can say is, this is the same thing as saying 4.35 grams of cobalt for every 100 grams of B12. Okay, that's what that means. It's that composition, parts per 100, grams per 100 grams. So that's a good starting point. Okay, so what's the mole ratio here? Well, the mole ratio is we're going to have to convert each top and bottom to moles, right? But we don't have the formula for B12. Okay, so that's the wrong approach. But if we do have this many grams of B12, then we can find out how many moles of cobalt we have. How about that? All we need is the molar mass of cobalt, which is 5593. Okay, so 4.35, oops, 35 here, and then 55.93 divide, that's 7.78 times 10 to the minus 2 moles of cobalt per 100 gram sample. Okay. Let's see. Oh, I forgot to write the number up there, 72. Okay. So figure out where we're starting from. We also know is that, let's see, 1 cobalt per molecule. We do know that there's 1 mole of cobalt for every mole of B12. Right, we do know that. So with this ratio, and if we know that many moles, moles of cobalt, if we know that ratio, then we can use this to convert that to how many moles of B12 are actually 100 gram sample. But I can't use it this way. I need to flip it. B12 cobalt. Now I can use that 7.78 times 10 to the minus 2 moles of cobalt. Okay. Moles of cobalt cancel. That tells me how many moles of B12 are represented by this many grams of a sample. And there we have our two things. Okay. So that tells me that 7.78 times 10 to the minus 2 moles of B12. So the molecular weight is going to be grams on top. 100 grams of B12 are this many in minus 2 moles. So 100, flip it and divide. Oops. I did something wrong. Flip it. There we go. Nope. There we go. 1286 grams per mole. All right. I missed it somehow. How did I miss that? 0.73. Oh. I think I miscalculated up here. Let's do this again. 55.93 for cobalt. No, it's 58. That's where I made my mistake. And that should be, I think, 38. Yeah, 38. So this is 38, 38. And that division will give you 1355 grams per mole for B12. Wait a minute, that's not even highlighted. What am I doing? I'm wasting my time. Okay, these are blown up too big to show the whole thing. This is a pictorial representation. 73, A, B, C, D, I think maybe E. So take this molecule and say, what is the empirical formula? Well, that's the molecule. So the molecular formula would be 6 carbons and 6 hydrogens. C6H6. The empirical formula is CH. Right? Just the simplest whole number ratio. How about the next one? 2 carbons and 4 hydrogens. Simplest ratio there is 1 to 2. All right, let's scroll to C. We have to count these up. Let's see. Carbons. 1, 2, 3, 4, 5, 6 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens and oxygens. 1, 2, 3, 4, 5, 6. The simplest ratio here would be divide that whole thing through by 6. Right? 6, 6, 6. So it'd be C, H2O. And then the last one is carbon, hydrogen, oxygen. Yeah. 1, 2, 3, 4, 5, 6. 6 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens and 1, 2 oxygens. Oops. Will you write that? There you go. Okay. Simplify this one. Divide through by 2. So that's C3H5 and 1 oxygen. That's how you solve that problem. Okay, let's see. Now we're finally in chapter 4. I've already gone over 45 minutes. All right, chapter 4. All right, an unknown substance dissolves readily in water, but not in benzene. A benzene is a nonpolar solvent. So it dissolves in water, but not benzene. So that means that the substance has to be polar, because it won't dissolve in benzene, but it will dissolve in water. What type of molecules do you have? Polar, obviously, right? Like dissolves like. The polar one dissolves, water is the polar one, it dissolves the substance. So the substance has to be polar, and it won't dissolve in benzene, which means the polar versus nonpolar. Hold on a second. An unknown substance dissolves readily in water, but not in benzene. Molecules of what type are present in the substance? Yeah, that's right. Okay. Yeah, that's right. Polar. Has to be polar. Let's see. 5 and 6. Which of the following is not a strong base? Okay. Remember our definition of strength. It just means that whatever goes into solution completely dissociates. It's not talking about solubility. If a little bit of it goes into solution, but when it gets in solution, it goes, it's completely broken apart, then that's strong. Right? So what we know is that the alkali metal hydroxides, potassium, lithium, are strong. We also know that the alkaline earth hydroxides are strong. They're not as soluble, but whatever goes into solution breaks apart. So the calcium and the strontium hydroxides are strong. Oop, I just noticed a chat. Hold on a second. Oh. Okay. Let's see. All right. So by process of elimination, A, B, D, and E are all strong. So the only one left to answer the question is C. Ammonia is not a strong base. Ammonia is a weak base. So this one is the weak one. Which of the following is paired incorrectly? All right. Got A, B, C, D, and E, I think. All right. Strong acid. Is sulfuric acid strong? Oh, yeah. That's a strong one. HNO3. That's a strong acid. Nitric acid is strong, right? So that one is false. Barium hydroxide is strong. It's an alkaline earth hydroxide. Makes it strong. HCl is hydrochloric acid. It's a strong acid. Right? And E, weak base. We just identified the weak base as ammonia. Okay. So the one that's not paired correctly is nitric acid as a weak acid. It's not. It's a strong acid. Okay. 7. The man who discovered the essential nature of acids through solution conductivity studies is Arrhenius. Arrhenius discovered the essential nature of acids. He was working with acids and he proposed a theory that we're going to cover. I think it's in the second semester, actually, when we get into acids and bases in more detail. But Arrhenius is your man. About 9. .4 sample of HF is dissolved in water. 16.4 grams of hydrogen fluoride is dissolved in water to give 2 times 10 squared milliliters. 2 times 10 squared milliliters of solution. What's the concentration? In molarity. Look at the answers. The answers are in molarity. Right? Molarity means moles per volume in liters. So this has to be converted to liters, which would be what? Well, that would be 200 milliliters, right? Which would be 0.200 liters. But we need moles here. So what's the molar mass of HF? Well, fluorine is 19. And hydrogen is 1.01, so 20.01. So 16.4 and 20.01 divided into it is 0.8196. All right, so the molarity then would be moles 0.8196 divided by liters, 0.2. Which is 3 significant figures, 4.10 molar. Well, the nearest answer is D, 4.1. Oh, I see. This is only 2 significant figures, so yeah, that would be correct. 4.1 molar. Okay, 14. What mass of calcium chloride is needed to prepare 3.950 liters of 1.49 molar solution? All right, back to our definition. Molarity equals moles divided by volume. So we're looking for mass of calcium chloride, but we can't get mass from that formula. We can get moles. So if we solve for moles, then that's molarity times volume. All right. The molarity we need is 1.49 molar. And the volume is 3.950 liters. So that'll give us moles. At 5.89 moles, yeah, of calcium chloride. Now that we have moles, we can convert that to grams. We just need the molar mass of calcium chloride. So calcium is 4008. And 2 chlorines is 3545 times 2. Which is, that gives us 110.98. Go. So that value times 5.89 is 653. 3 significant figures. 653 grams of calcium chloride. Okay. All right, that was 14. 16. Let me switch markers here. See if this one has rested some. What mass of solute is contained in 256 milliliters of 0.838 moles ammonium chloride solution? So we have, we want to know the mass of ammonium chloride. Ammonium is that, the chloride is that. So that's the formula, right? 1 positive, 1 negative. We have 256 milliliters. We have a molarity of 0.838 molar. And we have 256 milliliters, which is what? 0.256 liters, right? The unit gets bigger, so the number gets smaller. And there are 1,000 milliliters in a liter. So we move 1, 2, 3. 0.256 liters. So the number of moles is equal to this number times that number. Is 21.45 moles of the compound. But the question was grams. So we need molar mass. What's the molar mass of that? Well, 14.01, 4.04, and 35.45. .04 is 1.01 times 4. . which is 5350 times 21 equals 11.5 grams of ammonium chloride. Okay? All right. Let's see, we can get those both on there. 17. All right. 74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.45 liters of solution. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide? This is a combination problem. First, you have to find out what is the concentrated stock solution value. What is its concentration? Then you can use a dilution ratio to get to the final answer. So first thing we have to do is 74.28 grams of barium hydroxide, and they're kind enough to give you the formula. Okay, dissolved in 2.45 liters. We need to know moles of this first. Grams per mole. So what's the molar mass of barium hydroxide? Barium is a big, big atom, 137.33. Like 2 oxygens, 32. 2 hydrogens, 2.02. So I add those together. 2 and 137.33. That's 171.35. Divided into 74.28 is 0.4334 moles of barium hydroxide. So the molarity of the concentrated solution is 0.4334 moles per 2.45 liters. Moles per liter. All right. 2.45. And that's 0.1769 molar. Okay. Now we know the molar concentrated molarity. The final molarity we want, the diluted molarity, is 0.1. Okay. What we don't know is the volume of the concentrated solution that we need to make up 1 liter of the diluted solution. So remember, concentrated times volume concentrated equals diluted times volume of diluted. So what do we have here? Well, we want this one. So let's see, this would be like that. Diluted times volume diluted over concentrated. Now we can substitute our values. This one is 0.100 molar. Volume of diluted is 1. Concentrated is 0.1769 molar. Our values are in milliliters, right? This is still in liters, so we're going to have to do another conversion. So 0.1 times 1 is 0.1, and divide by 0.1769 is 0.565 liters, which is 565 milliliters. There you go. $17. 18. Scroll just a little bit. Here we go. 18. What volume of 18 molar sulfuric acid must be used to prepare 2.3 liters of 0.145 molar sulfuric acid. Right, this is really simple. You have molarity of the concentrated equals 18 molar. The volume of the concentrated is unknown. Right? The diluted concentration we want is 0.145. And the volume, the final volume of the diluted sample is 2.30 liters. Okay. Now, if we use our ratio here with these units, we're going to come up with liters. Our answer is in milliliters. So I suggest that we convert this to milliliters, right? 1, 2, 3. Right? 3, 0, 0. Now our answer is going to be in milliliters. All right, so MC BC equals MD BD, and we want this one solved for, so MD BD divided by MC. So the diluted we want is 0.145 molar. The volume we want is 2,300 milliliters. And the concentrated is 18. So 0.145 times 2,300 divided by 18 is 18.5 milliliters. Or rounded off. Let's see. Yeah, we're limited to 2. So rounded off to 19 milliliters. Okay. That's 18. Lots of repetition in here. And there are a lot of these examples where you're trying to decide what type of reaction it is. We're going to do several of them, but not all of them. All right, we're going to go down. It's better stick with this 28. Now we're going to identify what type of reaction it is. And since this is multiple choice, all of the types of the reactions may not be in your answers. Right? So if you decide that it's a certain type of reaction, several different types, then you look for the ones that are there and pick those. And so 28. What type of reaction is the first one? Well, notice that you've got 2 aqueous solutions. Yeah, 2 aqueous solutions, zinc 2 bromide with silver nitrate. And it yields a solution of zinc and nitrate and a precipitate of silver bromide. That is a precipitation reaction. Right. So the following reactions, both of them, let's see, how about the second one? Yeah, 2 aqueous solutions. We get a precipitate and a solution with spectators in it. Okay, so both of these are precipitation reactions. Neither one is oxidation reduction because you don't see a change in oxidation state for either one of them. Acid-base reaction, no, you don't have an acid or a base in that mess. Precipitation reaction is the only one that works. Let's see, 29, yeah. Okay, 29. How do we classify each one of these? Well, let me see. We've got aluminum and bromine make aluminum bromide. So that's a combination reaction or a synthesis. Silver oxide yields silver and oxygen. That's a decomposition reaction, right? So we can't select one or the other. CH4 and O2 yields carbon dioxide and water. That's a combustion reaction. But remember, all combustion reactions are oxidation reduction. How about the first two? Notice that with aluminum on one side, as as a free element, but it's in a compound on the other side, that's an oxidation reduction. Similarly, this one is a compound on the reactant side, and there's element on the right-hand side. So the last one is a combustion, oxidation reduction by default. The first two are both oxidation reduction because you have element compound. Right? That rule will also tell you that these are all redox reactions. Right? So that would be, let's see, oxidation reduction. A. All right. Let's see, what about this one? Which of the following salts is insoluble in water? All you have to do is look up the in your chart, right? Right, and this will be on the exam, right? This chart in the back, right? So you just find the cation across the top, follow it down until it reaches the row with the anion in it, and see if it's grayed out. Sodium sulfate, right? Sodium sulfide, excuse me. Sodium sulfide is soluble. How about potassium carbonate? Well, if I want potassium down to carbonate, it's soluble. How about lead nitrate? Lead 2 nitrate. Follow it down. It's soluble, right? I'm just reading them off the chart. Calcium chloride. All right, there's calcium. Follow it down to chloride. It's soluble. All of these are soluble. Right? There are none of them insoluble. They're all soluble. How about 37? All right, consider an aqueous solution of calcium nitrate added to an aqueous solution of sodium phosphate. What's the formula of the solid formed in the reaction? Well, let's see. If we have calcium nitrate, right? 2 plus ion, minus 1 ion, calcium nitrate. And we're going to add it to what? Sodium phosphate. How do you tell what possible products could occur from here? This is a double replacement reaction. Take this one and combine it with that one. Take this one and combine it with that one. How about sodium nitrate? Is it soluble? Indeed it is. So look it up in that chart. You'll find it soluble. How about calcium phosphate? Right? Look it up. That one is insoluble. It forms a solid. Okay? So, of all these that you have to select from, you got to be able to write it correctly too. This is a 3 minus ion. This is a plus 2 ion. So 2 goes over here and 3 goes over there. Okay? So C would be the correct answer. That's the solid formed in this reaction. All right, 38 and okay. These are all what? Aqueous solutions of barium chloride. Let me scoot that back a little bit. And silver nitrate are mixed to form solid silver chloride and aqueous barium nitrate. The balanced molecular equation contains which of the following? The balanced, and that's 38. 39, the balanced complete ionic equation contains which of the following? And 40, the net ionic equation contains which of the following? So to answer 38 through 40, we need to write those 3 sequences of reactions for expressions for this one reaction. Barium chloride and silver nitrate. Barium chloride plus silver nitrate. Right? I know that's right because this is a minus 1, that's a plus 2. plus 1 minus 1. So what do we get from these? All right, we get silver and chlorine. And you look it up, and that's a solid. And then we have nitrate and barium. We need 2 of these. And that is soluble. All nitrates are soluble. Now we need to balance it. All right. We have 2 chlorines here. We need 2 chlorines there. But that gives us 2 silvers. So we have 2 silvers here. And that gives us 2 nitrates. And we have 2 nitrates, 1 barium, 1 barium. That's the balanced, complete, or molecular equation. So which of the following terms are contained there? Well, notice that in your answers, the coefficients are included, right? So the term that you're looking for, silver chloride, no. 2 silver chlorides, yes, solid, that's true. 2 barium nitrates, no, that's not there. 1 barium nitrate, 1 barium nitrate aqueous. Well, you know that one's there too. Which of the following terms? Wait a minute, is there an error in this? Oh, wait a minute. No, excuse me. 2 nitrates. BaNO3 is not right. And they're not 3 silver chlorides. So the only one that's there is B. 2 silver chloride solids. Now for the next one, the complete ionic equation contains what? In that case, we take the aqueous solutions, which we know are separate ions, pull them apart, and write the complete ionic equation. I'm going to start way over here. So we have barium 2 plus aqueous plus 2 chlorides plus 2 silvers in solution and 2 nitrates because of that coefficient. 2 nitrates. Okay. Now this solid stays the same. It's not broken apart. It's a precipitate. Then we have 1 barium 2 plus and 2 nitrates. There we go. That's the complete ionic equation. So which terms are there? 2 Ba2 plus. No, there's only 1 of them. 1 chloride. No, there are 2 of them. C, 2 silver. That's there, right? This is there. 1 nitrate. No, there are 2 nitrates. Silver chloride aqueous. No, it's a solid. Right. So this is the only one that can be C. So this one was B for 38, 38, B, and 39, C, correct? Yep. Now the net ionic equation is what? For the net, you eliminate the spectators. What's on both sides? Barium, barium. That's gone. Nitrate, yep, nitrate's gone. Silver chloride is formed from these 2. But now look what's happened. Now we have a net ionic equation with 2 chlorides, 2 silvers, and 2 silver chlorides. We want the simplest whole number ratio, which means we need just 1 chloride, 1 silver, yields 1 silver chloride. So this is the net ionic equation for number 40. All right, so we have 1 silver. Yes, A is correct. Barium's not there, nitrate's not there, hydrogen never was there, and silver chloride aqueous never was there either. All right, so this one is, what did I say? A? Yeah, A. Down right there. That's the trick to this one. Once you've eliminated the spectators, you find that now you need to reduce it further. Simplify it. All right. We're down to 45. When solutions of strontium chloride and sodium sulfate react, strontium chloride and sodium sulfate. So this is 2. How about this one? Strontium is 2+, so we need 2 of those. Which of the following is the spectator ion? All right. So what we want to do is find out, first of all, which one is the precipitate? Is there a precipitate? Strontium sulfate. Let's look that one up. Strontium here, down to sulfate. Yep. So SrSO4 precipitates. And what's left over is sodium and chlorine. Sodium chloride. Okay? Right, but we know that this is in solution as those ions. This one is in solution as that ion and that ion. And this is strontium and chloride. Aqueous. Aqueous. We didn't balance the equation, but it's only asking us which of these are spectators, right? We find that the chloride's the same on both sides, the sodium's the same side, both sides. So the sodium ion and the chloride ion are both spectators. Which one do we have to choose from? Well, B is a chloride ion. C is a sodium ion. Strontium and sulfate are not spectators. They're participants. So 2 of these are correct. The sodium and the chloride are spectators. All right. 50. What mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar H2SO4? All right, for this one, if you're going to be doing a whole lot of acid-base reactions, it may be useful for you to become comfortable with the concept of normality. But in lieu of normality, if you have a balanced equation, you can work it out that way also. This is 50. And this is a foolproof way to do it. So we got sodium hydroxide and sulfuric acid reacting together. Produce what? Acid bases always produce a salt, sodium sulfate. And that's soluble, plus water. Okay, so what we need to do first is balance the equation. We got 2 sodiums over there, we need 2 here. Now we have 2 hydroxyls and 2 hydrogens, right? And they produce 2 waters. So we need 2 waters. And that's balanced. Okay, now the question is, what mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar? Right? This is a stoichiometry problem. We can't move anywhere until we have moles. So how do you get moles out of that? Remember, molarity is equal to moles divided by volume. So moles is equal to molarity times volume. If we multiply volume times molarity, in this case, we've got milliliters. So what's our answer going to be in first? It's going to be in millimoles. So 25 times 2.7 is 67.5 millimoles. But in order to move, well, We could say millimoles over here, but eventually we're gonna have to use molar mass. So we might as well convert it to moles now. So how many moles is that? 1, 2, 3, 0.0675 moles of H2SO4. Right. Let's convert that to sodium hydroxide. H2SO4, sodium hydroxide, and the conversion factor is 2 to 1. So 2 times that value is 0.135 moles of sodium hydroxide. So now we just need to convert it to mass. Moles on the bottom, grams on the top. So what's the molar mass of sodium hydroxide? Well, sodium is 23. Oxygen is 16. Hydrogen is 1.01. So that's 40.01 grams per mole times 1.35 is 5.4. Let's see, we're limited here. 5.4? Yeah, 5.4 grams. So, there it is. Number 50. Now that reaction, that's how much do we actually need? Okay, never mind. 5.4 grams is the answer. We'll leave it at that. How about 52? In which of the following does nitrogen have an oxidation state of +4? All right, so here we have to be able to calculate oxidation states. HNO3, NO2, N2O, NH4Cl, and NaNO3. 2, excuse me. 2. Sodium nitrite. Okay, nitrogen oxidation state. So which ones do we know? We know this one is +1. We know this one's a -2. So that's a -6 and a +1 equals -5, which means this nitrogen has to balance that with a +5. Right, so A is not it. NO2, -2, -4. This one has to balance it with a +4. That's a good one. Well, we found our answer, right? Because there are no oddballs in there. If we did the rest of them, -2 here means that a +2 between these two would be a +1. The easiest way to do this one, that's an ammonium ion. So if we say +4 for the hydrogens, and we hold one of them out, we only need the +3 balanced with a -3 for that nitrogen. This one is nitrite, NO2 minus. So if this is a -2 times 2 is a -4, then this one, we only need -3 to balance. So this is a +3. Right. So here's your answer right here. '53, the oxidation state of iodine. 53 in IO3 minus, correct? Yeah. What's the oxidation state of iodine? Well, oxygen is -2 times 3 is -6, but we're going to hold one of those minuses out for the charge. -5, so this is a +5, which would be D. Let's see, 55 and 56. Which of the following statements is not true? A, when a metal reacts with a non-metal, an ionic compound is formed. True. That's just the nature of the beast. Metals and nonmetals make ionic compounds. A metal-nonmetal reaction can always be assumed to be an oxidation-reduction reaction. A metal-nonmetal reaction. Okay, we have to assume, to answer this one, that it's a metal elemental metal with an elemental nonmetal. Yes, that is an oxidation-reduction reaction. Our example is sodium plus chlorine gas. Transfer an electron over here for each chlorine. And that happens with metals, nonmetals. How about C? Two nonmetals can undergo an oxidation reduction reaction. Yeah. Oh, yeah. For instance, hydrogen plus oxygen is water. Right? So we have, let's see, 2 here and 2 here. Right? The oxidation state here is 0 and 0. Over here, it's -2 and +1. Right? How'd they get there? They transferred electrons. Well, C is true. How about D? When two nonmetals react, the compound formed is ionic. False. Two nonmetals neither one has the wherewithal or the desire to either give up or extract an electron from the other. So they share. So that's not an ionic compound. That's a covalent compound. So D is false. We found our false one. E should be true. Metal-nonmetal reaction involves electron transfer. We already said that one in this 56. All right. In the reaction, 2Ca, 2 calcium plus oxygen gas yields 2CaO solid. Which species is oxidized? All right. Oxidation state here is 0, 0. -2, +2. So what's oxidation? Oil rig. Oxidation is loss. Which one lost electrons? Calcium went from a 0 to a +2. It had to lose 2 electrons per calcium. That's oxidation. So calcium, C, calcium element was oxidized. '57. In this reaction, let's see. Yeah, this reaction. Cesium plus chlorine gas. 2 cesium plus chlorine gas yields 2, like that, like that. Cl2 is what? Well, these are 0, 0. This is a -1, this is a +1. That's an alkaline metal, so it's +1. So cesium would go from here to here. It is oxidized. Chlorine would go from here to here. It is reduced. Okay. The one that's oxidized is a reducing agent. The one that's reduced is an oxidizing agent. Okay. So the reducing agent, let's see, chlorine, this one, is an oxidizing agent. B. Now, is it oxidized? No. Is it an electron donor? No, it's an electron acceptor. It accepts an electron from this one because it's reduced. All right, so the only one that's right is it's an oxidizing agent. '61. We're running out of steam in here. Which of the following statements are true? Oxidation and reduction. Let's see. A, B, C, D, and E. About A. Oxidation reduction cannot occur independently of each other. That's true. They always occur together. They accompany all chemical reactions. Nope. Not necessarily. Describe the loss and gain of electrons respectively. Oxidation is loss, oil. Yes. Reduction is gain. Yes, that's true. Results in a change in the oxidation states of the species involved. That is also true. A, C, and D are true. There you go. '61. 63. Okay. Balance the following oxidation reduction reaction using the oxidation number method. All right, so we start off with Fe, Br2, and we end up with Fe3 plus and Br minus. Okay, what do they mean by, in the balanced equation, the coefficient of Br minus is what? All right, to use an oxidation reduction version, you need to first determine what the oxidation states are, 3 plus, 1 minus. So what happens to iron? Iron has a loss, 3 electrons per iron. Bromine, on the other hand, has a gain of 1 electron per bromine. So what does that mean? That means that our electrons don't balance. We need to balance our electrons, right? But we've got 2 bromines here. If we put another bromine here, that only gives us 2 electrons, and we've got 3 here. So we have to use cross multiplication. In other words, what we need is we need to find a common denominator. 3 doesn't work because of that 2. So the next one up is 4. But that doesn't work because of this 3. So what's the common denominator between 2 and 3 is 6. So if we say times 6 equals 6 electrons, and times 2 equals 6 electrons, how would we get that? Well, we put a 2 here and a 2 here, and we put a 3 here for 6, and we put a 6 here. Okay? That will give us exactly the same number of electrons, right? 2 times 3 gives us 2 there. 6 bromines gives us 6 electrons and gives us 6 bromines there. So the Br minus has a coefficient of 6. We ought to be getting close to the bottom. 66. Select the spectator ions for the following reaction. All right. PbNO3, PbNO3, 2. This is aqueous, obviously. And then KCl, 2 KCl. We don't write aqueous, but obviously it is. PB, you know what? Yeah, okay. PbCl2. Now, is that one a solid? That's the question. Because we know that potassium nitrate is not. It's aqueous. All right, so we need 2 of these. We need 2 of those. And let me see if I'm right. Lead 2 chloride. Is it a solid? Is it precipitated? Lead 2 down to chlorine. Yep. Lead 2 chloride is a solid. So the spectators are the ones that the ones that contributed to these, we have to keep. We got to keep this one, and we have to keep that one. Right? So the spectators are the nitrate ion and the potassium ion. Okay. So A says potassium and nitrate. There it is. That's it. Those are the only, these are the spectators. They don't enter into this part of the reaction to make the precipitate. They're still in solution on both sides. "66, 68, and 69. Identify the precipitate formed if any, in the following reaction in aqueous solution. So in aqueous solution, we have FeNO3 taken twice, which means this is a +2 ion. And then we're going to combine that with ammonium carbonate. Right, and this is a +1 total, this is a -2. All right, so if we combine iron and carbonate with a 2+ and a CO3, 2-, that one is a possibility. The other one, ammonium nitrate, is soluble. That is aqueous. So the question is, iron 2 carbonate, does it precipitate? And let's see, iron 2+, go down, follow it down to carbonate. Yep, that one precipitates. So B is the answer to this one. "68 and 69. I need to get another marker. Here you go. Here. In which of the following does nitrogen have the highest oxidation state? All right, we should have kept those numbers up there before. So this HNO3, this is a -2, -6, this is a +1, that's a -5, which has to be balanced by a +5. And I think we found out that B was a +4, N2O was a -1, +1. This is the highest number, +5. You can also look, well, I wouldn't suggest it. You need to be able to calculate those. But if you look at nitrogen in your periodic table, the highest oxidation state shown in the periodic table is +5. So that's as high as it gets, usually. "71. In which of the following does iodine have the lowest oxidation state?" All right. B, C, D, and E. I2O, I2O2, and iodine. Okay. All right, lithium's going to be +1. It's an alkali metal. Oxygen's a -2, so it's a -6, and a +1 yields a -5, which means a +5 for that. This one's a -2 times this -4, so this is a +4. This one's a -2. This one needs to be a +2, but divided between two of them means it's a +1. Iodine here, this ion is a +1, so this has to be a -1. And this one is 0. So the lowest oxidation state here is -1 for this compound. All right. Let's see. Is that it? That's it. Okay, we're done. And I'm only an hour and 45 minutes over. Stop the share. And most everybody's gone, but if you have a question, I'll entertain questions now. Otherwise, I'll see you on Tuesday. And we'll have the exam and then follow it up with chapter 5, gases.